Hi, good afternoon, everyone. My name is Marc Gaunt. I'm the Segment Marketing Manager for Eaton in the UK. And welcome to our webinar this afternoon, which is on the topic of arc fault detection devices. So just before we get into the webinar itself, just wider introductions. I've also got Paul Norris on the webinar with me this afternoon. So Paul's our Technical Standards Manager. At the end of the webinar today, hopefully we'll be able to answer any questions that you've got. There is a live chat that we've got during the course of the webinar, but so we'll look to try and save any questions until the end or to answer those questions, but feel free to chip in with anything as we go through the webinar. So before we get into the webinar itself, just very quickly a little bit about Eaton as a business. So we are not just an electrical business, we are a power management business that spans across both the electrical and mechanical sectors, so with footholds in automotive, aerospace and the wider electrical industry. We are a global business, but in terms of the UK, we employ in the region about 4,500 people with 31 sites in the UK. So it's very quickly just a little bit about Eaton as a company. So the webinar this afternoon, as mentioned, is on the topic of arc fault detection devices. It is a CPD accredited webinar. So for anybody that's taking place today, it will be CPD accredited. And the plan would be that we send CPD certificates to everybody within 2 weeks of the webinar today. So please keep an eye open in your inbox as the certificates will come through digitally, but your attendance will be registered with the CPD organisation. So in terms of an agenda for this afternoon, we have an hour planned to sort of cover through the topic of arc fault detection and to cover any questions that you may have. The broad agenda will be, we'll just give a little bit of a backdrop to arc fault detection devices and what's driven recommendations around that technology. We'll look at some of the statistics in the EU and specifically in the UK that have sort of supported some of these recommendations. We'll then recap on some existing technology that we already have within the UK in terms of electrical infrastructure, and then also get into arc fault detection technology a little bit more, what the benefits are and how the technology actually operates. Okay, so just as a bit of a backdrop, we expected that 2018 was going to be a year of some change within the electrical industry as we have the IT, update the IT wiring regulations coming along, the 18th edition. So with that change, we have new regulations coming through, and that normally brings about change with either installation practice or requirements or recommendations about the adoption of new technology. What we didn't understand until sort of middle of last year, though, was around the wider changes that are likely to take place in UK construction regulations as we move forwards on the back of some tragic events that we saw in Grenfell in the summer of last year. So as of today, we have the 18th edition that is coming along in the summer of this year that will be then fully in place by January 2019. But in addition to that, unfortunately we saw the tragic events of Grenfell, and then on the back of that, we've seen the Hackett report that was sort of launched, and the initial findings of that were released sort of a few days ago. So the Hackett report is now available to view. There's much discussion going on around that, but that's likely to influence building standards requirements as we move forwards. There's also further investigations that are going on around particularly higher risk residential buildings, so specific investigations into private rented accommodation. And then more widely, we've sort of seen other sort of governments, so the Scottish government, where it's sort of started to look at sort of fire regulations and put into place or mandated requirements around the use of smoke alarms within homes. So we knew 2018 was going to be a year of some change, but there's sort of further events which unfortunately have sort of taken place that are then likely to drive further changes within regulations as we move forwards, which, as we'll come on to, are very relevant when we talk about arc fault detection devices. So when we look at statistics, and we'll also look at Europe first and foremost, we consider that we have a really good level of electrical standards in the UK, and more widely within Europe. There are arguably some of the best engineering practices that there are within more on a global basis. But despite that, if we look at sort of general statistics from FireSafe Europe, there were still typically 2 million fires that were reported each year at a European level. 90% of those fires that took place within buildings. There were sort of somewhere in the region of 4,000 people that were killed within Europe as a result of those fires. And as well as sort of the people cost, which is really important. There was also the financial cost at a European level, which was estimated to be in the region of 126 billion euros. So, despite some of the standards that were placed both in the UK and at a European level, we still see these occurrences of fires within buildings. If we then sort of look within, I suppose, our own industry then, and the electrical side of the industry, it's estimated at a European level that somewhere in the region of 25% of fires that took place, that electricity was the source of those fires. So there's a high proportion of them where it actually can be attributed back to an electrical fault of some nature. So if we then look closer to home, and then sort of in the UK, and some statistics within England, because the stats are reported separately for England, Scotland, and Wales. But in the UK, in the last reported year, up until June 2017, there were some 200,000 fires reported in the UK. And then if we look in England, 38,000 fires that took place within family accommodation, over 1,200 fires that were within communal living areas, 600 fires that took place within hotels and hospitals. And unfortunately, as a result of that, there were 346 fatalities that were reported in England alone. So then again, if we look within our industry specifically, there was somewhere in the region of 29,000 fires where electricity was deemed as being the cause of that fire, and in the region of about 8,000 fires where it was a result of some sort of faulty appliance or lead. So I guess the point that we sort of that we're trying to get to with this is that each time we have a release to wiring regulations or an update to building standards, it's about sort of typically raising the bar and looking to how we can make things safer within buildings. So what we see today is that there is a level of safety within buildings, but despite that, there are opportunities to potentially increase safety further, and particularly around sort of fire safety within buildings, which is sort of really relevant within the UK today. So we're just going to start to talk about technology a little bit now, and just to recap on typically what we might see within a building in terms of circuit protection and how that can protect the occupants of a building. So today we might sort of typically see three levels of protection when we look at electrical safety. So the first of those levels, and the most basic format, is some form of mechanical protection. So some form of insulation that sits on live parts, or an enclosure that prevents access to live conductors. What we see then laid over on top of that is some sort of fault protection against overcurrent by way of an overload or a short circuit within an installation. And as we've seen progressively within the UK over the last 30 or 40 years, we've seen a move from fuse-based technology to typically miniature circuit breakers, and that technology moving on further, again more recently, with the introduction of RCD technology. So in the UK today, what we sort of think of when we think of sort of protection technologies with buildings is first and foremost some sort of enclosure system. We then have overload and short circuit protection in sort of final distribution via an MCB, and that then may be complemented by RCD protection as another layer of shock protection, as an out-and-out RCD, or by combining technologies with RCBOs within buildings. So what do those technology protect against? So touched on some of this already, but that could be an overcurrent within the circuit. It could be a short circuit between live conductors, or it could also be some sort of earth fault based, which could be detected through overcurrent. So it could be picked up by an MCB, or if it was a lower level earth fault, we also see RCDs that would afford some sort of protection in that area as well. So that protection we've seen increase over the years. We've seen new technology come in, and as I mentioned before, particularly within commercial buildings, we've seen that technology starting to combine within RCBOs, and also within residential properties more recently, we've seen the adoption of RCBOs grow within residential properties as well. So we've spoken about what we have within buildings today in terms of technology and what it protects against. But there is a fault today where that technology doesn't necessarily detect that a fault is present, and therefore cannot protect against the effects of that fault. And that is that type of fault is what we refer to as an arc fault, and this is where arc fault detection devices become more relevant. So, first part we'll talk about what is an arc. So an arc we can think of as some sort of micro lightning that could ultimately lead to a fire within a building. It can take place within the fixed infrastructure of a building, so a fixed circuit that might run in a wall, within a ceiling, or a floor. But equally, it could be within a trailing lead, or it could actually take place within a load as well that's connected to that infrastructure of a building. So those arc faults, they could be detected by technology that we have within a building today, but as we'll come on to, in many cases, they might not actually be detectable, and therefore the effects of those faults we can't prevent against. So we've spoken about what types of faults we might see within buildings today that we can protect against. So what are the types of arc faults that we could see within a building? So the first type of fault that we might see is what we refer to as a serial arc, where we've got an example of that on screen. So that's something that could be between the live conductor itself, between the neutral conductor, or between the earth conductor even. And what we typically see there is that the level of fault is such that we wouldn't expect an MCB, for example, to detect that fault and therefore trip. The reason for that is we're talking about a high resistance fault. So we've still got current flows taking place. We've got heat being generated in the case of that fault, but it's high resistance, therefore it's not a high level of current, and that fault would not typically be detected by an MCB. We then have parallel arcs, so that's what, as shown on screen, could be between live and neutral conductors. Again, typically a high resistance fault where we wouldn't expect an MCB to detect it, and therefore that fault would not be disconnected. And then the last type of fault that we're just showing up on screen is a fault between live conductor and protective earth, where if you've got, for example, a 30 milliamp RCD, if that arc fault was above 30 milliamps, we would expect the RCD to trip. Again, if it was below 30 milliamps, or if you did not have RCD protection on that circuit, we wouldn't expect that circuit to be disconnected. So that's a little bit about what is an arc fault and the types of arc faults that we could see within a building. So why do we need to protect against arc faults? Well, as we've mentioned already, arc faults, they can take place in a number of different scenarios within a building. And typically we tend to find they're hidden and not necessarily obvious faults that could be detected. So that's the first point to bear in mind. They're not detectable in terms of their general nature, but because they are high resistance faults, we don't tend to get this high level of current flow. And again, there's not an obvious thing that takes place in the building where you've got a circuit that's disconnecting. Also with arc faults, it's something that that can occur over the general passage of time. We'll come on to this in a little bit more detail shortly. So as a building and its infrastructure gets older, we can see that there's a higher potential for arc faults taking place. But also if there is remedial work that's going on within a building, an extension to that building, it can introduce further risks where there could be a higher probability of an arc fault taking place. And just coming back to the last point we've got on screen, what we can find with arc faults is we can have something where it can take place and it can be there for quite an extended period of time, not be detected and get to a point where it does then introduce risk within the building. So some of the most frequent causes of arc faults that we see more widely. So first one is around crushed wires. So if we look at portable appliances, got an example up on screen. If you've got some sort of extension lead in place, for example, that lead becomes crushed, then that could introduce an arc. If we've got some sort of remedial work going on, as I mentioned, or even DIY work, it could be the risk that we introduced there is where you could pierce a cable, could nick part of the insulation, and as a result of that, we run the risk that we could introduce an arc fault within that circuit. We then come on to the aging of the installation itself. So as the installation gets older, we can potentially see we get heat within circuits, within end loads as well. We could potentially see the breakdown of insulation, and that process of aging increases the risks of arc faults. Even if exposed to UV rays can introduce a potential risk within a building. And then other sort of potential occurrence of arc faults can come through rodent infestation. So I've certainly seen something on social media recently in a rural community. I think it was a barn conversion where they'd had a rat infestation. They'd lost power to a circuit. Local electrician had gone in, and it became very evident the result of that was this rodent infestation. So in that particular case, was something very evident that was wrong with the installation, because that circuit had disconnected. But it could have been that before that full disconnection took place, there was an element of arcing that took place in that building and could have introduced a risk to it. And then, the last potential scenarios we might have is something where the general wear and tear of connections could introduce an arc, or mechanical damage that's sort of taken place during the life of that circuit, and we've got an example of that, could introduce a risk. So arc faults, the root cause of them, there's a number of different scenarios where they can take place. It can be the general passage of time, or it can be a specific incident that leads to that arc fault taking place. So we'll just talk about a real example now, and I have to confess that it's actually one that was taken from my home. So the scenario was that for a period of time I actually ran an electric vehicle, and for anybody that has one, you will know that when you receive your electric vehicle, for most manufacturers, they provide a charging pack which plugs into a 13 amp socket. It's not the most desirable way of doing it, but as a means of providing power to the car, at least initially, it's it's a means of getting power into that vehicle. So I used that charging pack for a period of time until my full charger was installed. And what actually happened in this occurrence was that unfortunately I damaged the plug that was feeding that charging pack. I removed the plug and basically replaced it. Unfortunately, what I didn't realise at the time is that I'd done a pretty poor job of actually rewiring that plug. I fitted the plug, plugged it in, charged the vehicle overnight, came back into the garage the next day, and the first thing I was met with was a smell of that if you work within the electrical industry, you'd probably recognise, where we wouldn't describe it as a burning smell, but almost like a burning smell, but a breakdown of insulation of some form. We tried to work out where it's coming from and realised that it was from the general vicinity where the car was plugged in. Switched off the socket concerned, and then removed the plug. And if you can make out the image on screen, it's actually the socket on the left-hand side. And what actually took place was when I unplugged the plug from the socket, one of the pins actually stayed within the socket, and the rest of the plug then came out. What had actually happened is overnight, when charge was placed onto the vehicle charged, but because it was a really poor connection, you got this heat that was generated within the plug itself, to the point where it actually eventually burnt through. So it's a real example of poor workmanship on my behalf, and the results of that you can sort of see on screen on the left-hand side, where actually there's this arc that was introduced within that particular circuit. So what we actually see within arc fault detection is this missing link, where it's this extra layer of protection within buildings for faults. I mentioned briefly before the Hackett report. It's worthwhile reading if you've not already had it. It's something in the public domain. You can download it. There's a pretty good summary at the front of it. And within the Hackett report, to say first and foremost, with the Hackett report, it's something that's been debated quite heavily over the last week to 10 days. From my personal point of view, there's some really good recommendations that are in there. I think when you look at it more widely, one of the points that's been mentioned is, does it go far enough? But I think one of the points that Judith Hackett mentioned is that there is no silver bullet when it comes to building safety. So I would say with arc fault detection, it's not a silver bullet. It doesn't cover all aspects of building safety. But what I would say is that something that the Hackett report refers to is layers of safety. and we would absolutely say that we believe that arc fault detection technology is another layer of safety we can put within buildings, and it is further evolution within the wiring regulations. And I think the other point as well that Dame Hackett refers to is around risk assessment within buildings. So we'll come on to this in a little bit more detail shortly. So what we would suggest is when we look at arc fault detection, we should look at what's the risk within the building, and that's when the drive is then about whether we should choose to use this technology or not. But for us, when we look at the evolution of technology, we've had live conductors enclosed for many years. Overcurrent protection technologies evolved. We've seen more and more adoption of RCD technology, and we now have this arc fault detection technology which is available to us that sits above those existing technologies, which we could consider where we perceive a higher risk within a building. So at that point, we'll come on to a bit more detail about the 18th edition, what will sit within that around arc fault devices, and what the recommendations that we will see when that is actually published. So the first point I mention here is that arc fault detection technology is not actually new. So when we look at Europe, in Germany, it's actually mandated when we look at certain applications within Germany. And then what we actually see is when we look at other countries within Europe, there's a progressive move towards arc fault detection technologies, either a requirement or a recommendation. Outside of Europe, and we'll come back to this, it's actually also mandated in the US, in most states now for certain applications, and also has also been used within Canada for many years as well. So actually, when you look at the US, a version of arc fault technology, so it's what is referred to AFCI technology, has been either recommended or required for over 20 years now. So although it's relatively new to us in the UK, it's actually technology that's been used within other countries for over 20 years. But for us in the UK, the first we will have seen of it is within the 18th edition of the wiring regulations that will come along in summer of this year. So the specific requirement that will be, or regulation should I say, which is relevant to arc fault detection devices is regulation 421.7, which we fully expect now will be introduced to recommend the use of arc fault detection devices and mitigate the risk of fires in final circuits of a fixed installation. So it's regulation 421.7 that will talk about recommendations for arc fault detection devices. So I did correct myself just now, and the reason for that is what I should mention, there is not a requirement within the 18th edition for the use of AFDD devices. There is a recommendation for the use of them. So the question that we tend to have at that point is that there is a recommendation. So what does that recommendation apply to? Probably the way I would summarize it is it's generally a risk-based recommendation, and it looks at either the risk to the occupants of the building, or it looks at the risk based on the construction of the building, or it looks at the contents of the building itself, or it could be a combination of those things. So around the risk to occupants, that could be based on the nature of the building and typically really where that involves sleeping accommodation. So the Hackett report refers to what are called HRBBs, high-rise, or HRRBs, should I say, so high-rise residential buildings. And Dame Hackett now has referred to those as being a high-risk building. So that's what we might refer to more widely as a multiple occupancy dwelling. So the Hackett report focuses specifically on those type of buildings. Interestingly, it also refers to student accommodation and hotels as well as being buildings where we have people sleeping overnight, and it could also be where there's a lack of familiarity with the layout of that building as well. So what we may see is with future or impending building regulations, there will be a specific focus initially on HRRBs, but the Hackett report does suggest that these other higher risk buildings should be brought into scope and considered specially as well. So the next type of buildings where arc fault devices are recommended is around the characteristics of the buildings. So that could be where we have, for example, materials stored where they could be highly flammable. So that could be a barn type installation, it could be a workshop of some type, or it could be some industrial application where we've got highly flammable materials that are stored. So that's around the characteristics of the buildings themselves or where they're being used. We've also then got the construction of the building itself. So if you've got something like a thatched building, that could be really relevant to arc fault detection devices. And then the last point is around the risks, the contents. So if you've got applications like museums, libraries, art galleries, where they have artifacts that are not replaceable, those are the type of buildings where the use of arc fault detection devices are recommended. So we've spoken about regulations, we've spoken about what the 18th edition will recommend. We'll now talk a little bit about the actual technology itself within arc fault detection devices. So an arc fault detection device actually is available in a number of different sort of footprints depending on the manufacturer. So arc fault detection devices are not an Eaton technology, so hence why this is a CPD presentation. This is not an Eaton pitch, it's a generic technology in the same way we would talk about an MCB. AFDDs are generic, but they are available in different formats. So they can be standalone, so they can be just a standalone device which acts as an arc fault detection device, or it can be combined with an MCB, or it could be combined with an MCB and RCD protection, so what we refer to as an RCBO today, with that arc fault protection technology embedded within it. So just to give you a few visual examples of what that might look like, we've got again this sort of standalone arc fault detection device. We then may have something that might clip on to an existing sort of technology, or we've got something then which might be an all-in-one device where it sort of basically it covers off all the different forms of sort of faults that we touched on previously. So that's likely to evolve over time as RCBOs have done. But when we initially look in the marketplace today, you will see variation in manufacturers around what their arc fault detection technology affords. What you'll also find is that the actual specification will vary. So if we've got an all-in-one device, for example, what we'd start to look at now is what's the braking capacity, because it has an MCB element. We'd look at what's the sensitivity, because it has an RCD element, and then we have that arc fault element sort of sat on top of it. If it was just combined with an MCB, we just look at the braking capacity, and if it was standalone, that would just be what really sort of contains this arc fault element. So we've just popped up one example on screen where it's a device that would have all the technology embedded. And if we just use that one device as an example, we've got this overcurrent protection built into it. We've got earth fault protection, and then we've got arc fault protection. And if you just look on that image on the left-hand side, you've got the toggles, which we would normally see on an MCB or an RCBO. You've got a trip indicator at the bottom, which is not uncommon. We've got a test switch, or test button rather, up on the left-hand side, the little sort of yellow button you might be able to see. And then on the right-hand side, in this particular instance, we've got sort of a window that would give some indication of what is the nature of the fault that's taken place. I can see just a few questions sort of coming through on the left-hand side, just to cover one up around testing, which is a question that does come up quite commonly. So around testing, we would find for some manufacturers, the devices would auto-test when it comes to the arc fault element. So there would be, would still follow UK requirements around testing the RCD element, but the arc fault element may test itself. If there isn't this auto test function there, then if I remember correctly, and Paul, correct me if I got it wrong afterwards, the general guidance is to manually test them every 6 months if that auto test functionality is not built into the device. So that was one example about what an arc fault defect detection device looks like. One of the other questions we tend to we've had over the last few weeks and months, we start to talk about what is coming in the warrant regulations. Well, what does that look like when I think about my consumer unit or when I think about my distribution board? So again, the format of these is likely to evolve, and it would depend on the manufacturer. But actually, when we look at the consumer unit itself, we've got a consumer unit example on screen. At first glance, it doesn't look actually that much different to what your standard consumer unit would do. Again, for most manufacturers, when we use arc fault detection devices, the pitch of the poles, so that the buzz bar, can vary. So it may mean we have to put the arc fault detection devices on a separate leg, but actually the configuration is not particularly complicated. It could be a bank that sort of sit on their own. It can be linked off. They could be fed by an existing RCD, or in this particular case here, they're actually fed by the main switch, because we're using devices where they've got inbuilt earth fault protection as well as overload and arc fault. So the configuration of consumer units and distribution boards may evolve slightly. I'm sure it will evolve as we move forwards. But it's not, it's not a radical change around how a device would be enclosed within a consumer unit. So we'll just talk now about how arc fault detection devices work. So one thing we can say is around arcs is that we do see arcs in, I'd argue, probably every installation every day. So we operate a light switch, we're likely to see some arc that takes place. If we've got some sort of rotating machinery, we're likely to see an arc fault that takes place, an arc rather, not an arc fault, an arc that takes place on that particular circuit as well. So when we look at arc fault detection devices, really the way they operate is they are looking at the footprint of what is going on within that particular circuit. So what's the profile of what's going on? And the devices look at, I've got a sine wave in this particular case here. I've got arcing that's going on, but actually I know that that's a natural arcing process that's going on with that particular circuit. And arc fault detection devices are designed so that they will ignore that typical arcing that goes, a natural arcing that goes on within an installation. What they will look for, though, is anything which is more abnormal, where it is, an arc fault rather than a natural underlying arc. So they will, in summary, they will distinguish between natural arcs and the actual profile of an arc fault within an installation. It's also worth mentioning as well that as technology evolved, there can be some considerations, as there are with RCDs today, about DC components on circuits. And also things like power line adapters today. So it's worthwhile asking manufacturers if they've taken that on board, and do they consider it to make sure that if that sort of technology is being used, that arcs aren't masked in that process. But I would sort of say that again, arc fault detection devices is not specific to Eaton. There's some really strong brands that are out there, and they've carried out, I'm sure, some really sort of thorough testing around these sort of scenarios. So just to summarise the technology itself, it is available in a number of different formats, but it's really about sort of raising the bar further on safety levels. In the case we've got on screen, it's about providing overcurrent protection, it's about providing short circuit protection, earth fault protection, and now introducing another layer, this arc fault protection as well. The actual technology that sits behind it, it's a digital technology that we're using to sense the arc. We know that arcs take place naturally on circuits today, but we would distinguish between what is a natural arc and what is an actual arc fault, and look to disconnect the circuit if that is detected. And then just sort of just to close off about so why use arc fault detection devices. I think as a business, we are very sensitive to what happened at Grenfell last year. And as a business, we try and take a really balanced view about how that sits with what's going on in the UK. It is really relevant, but for us, it's not about climbing the back of that. It's about the WARN regulations. We're already looking at how we raise the bar, and now we have some technology where it's something that we could consider to prevent occurrences such as that in the future. But why use arc fault detection devices? It's at this point we come back to the US, which we touched on briefly earlier. So the actual use of arc fault detection devices goes back to 1999, I think it is, in the US, where for the first time, I think in the US, that's where NEC regulations referred to what is called AFCI, or arc fault current interrupters, which is a form of arc fault detection device. Those requirements have been progressively expanded, And the reason for that was that in 2011, the National Fire Protection Association in the US went away and did some investigation. And from the report, the work they commissioned, the report that came back, they estimated that out of 47,000 homes or home fires that they'd looked in that period, 50% of those could have been prevented through the use of arc fault technology. So it's probably now little wonder that as a result of that, as of today, or March this year, there were 48 states in the US where arc fault detection technology was mandated in new homes in the US. So we've got, in the US, it's gone from something where is a recommendation, something where it's required within certain states, and based on the experience of those states, I'd suggest, and then wider work that was done, it's then been adopted more widely within the US because of the level of impact that it was estimated that would have. The impact of that, I mean, one thing we do have to consider is that arc fault detection technology has been introduced progressively. It's been introduced for new homes, not existing homes as a mandatory requirement. It would only take place within new homes or where a new home is having some sort of major rewire. I think the stats are that over the last 10 years, I think from memory, it's that the incident of fires as a result of electrical faults has dropped by, I think it's 20% from memory. They're certainly seeing a downward trend. I think from the reports already, it can't all be attributed to arc fault detection devices. Again, we would sort of say it's a layer of protection. Arguably, one of the first things we'd look at is good workmanship, but it's seen as something which is driving that downward trend of arc fault, of fires as a result of electrical faults in the US. So for us as a business, we support what the wire regulations is due to recommend. It is a risk-based assessment. It's not a requirement, and we think that is a good way to approach it as a business as well. And when we look at other countries, we think those stats are a really good reason about why we should consider that technology in the UK. So just to close, and then we'll look to try and answer some of the questions that I can see we've had through the chat as we've gone through the webinar. There's two sort of areas I'd probably refer you to sort of for further advice on the topic. So I know that Voltman will be sharing this presentation after the event today. So if you've got a pen to hand, there's a URL just at the bottom of the screen there, eaton.com/LiveSafe UK, which is it's an Eaton website which is set up to support a better understanding of arc fault technology. So you've got a pen to hand, jot that down now. On that site, you can get video content, probably explain a little bit more about how the technology works. There are some case studies from other countries and white papers you can download as well about the technology. So that's a really good source of information. So if you've not got a pen to hand, Voltman will share the presentation with you afterwards, and that will be in there. The other site that I would refer you to is if you Google arc fault detection or AFDD guide, and then BEAM, B-E-A-M. So BEAM is an organisation in the UK which is supported and works very closely with a number of major manufacturers in the UK. There is a guide that BEAM have produced on arc fault detection devices. I think Paul was pretty instrumental in that, so Paul will cover some of your questions shortly. It's a really good impartial guide. It doesn't favour any one manufacturer. It does refer back to the wiring regulations as well. So that's a really good sort of source of information around technology, the different footprints we mentioned before, and type of buildings we might want to consider arc fault detection devices within. So at that point, I'd just like to thank you for your attendance today, just sort of listening to what we've just discussed. We're not closing the webinar at that point, but I'll reintroduce now Paul Norris. So I said Paul's our technical standards manager. I think you're going to help me pull together some of the questions we've had on the chat.
Yes, indeed. Hope you can hear me.
Yeah, we can hear you.
Okay, great. Yeah, we've got a number of questions come through. Let's just kind of work through these in order. There's been a question from on the Voltman website concerning commercial installations and whether they're only intended for commercial installations and only on certain circuits. The wiring regulations, when they come out, the 18th edition comes out, certainly at the moment, and unlikely to change. It not differentiate between residential and commercial. It's recommended as an additional protection against fire, and then lists a number of examples as to what kind of situations can be protected, what kind of installations can be protected. So it's not listing domestic or commercial, it's all down to the type of installation, similar to the list that Marc put up on the screen earlier with sleeping accommodation, wooden buildings, buildings of like museums with protected goods and such like. So it's not down to the type of installation, whether it's residential or commercial. It's down to the need for protection against fire and the type of construction and use.
So, Paul.
Yeah, sorry, go on.
Just to mention, I think we're having a couple of audio problems. So if just to add what you were saying, just to reiterate what you're saying to start with, I know the IT wiring regulations is coming out and the BEMA guide. It does refer. It tends to lean towards residential buildings to start with. I would suggest it's not solely those buildings, but as we touched on earlier, the Hackett report again starts at that point, but also brings into scope other buildings where it's what deems them as being higher risk. But I think the point is that it's deemed to be a risk-based assessment we should look at, and the risks where we should consider. And then one of the main ones is this point around how complex the building is, how easy it is to evacuate it. Really, I'd suggest what that is leaning towards. And if you've got people sleeping within a building, there's an extended period of time to alert people and get them out of that building more safely as well. I think there's a question about testing of arc fault detection devices. I think we covered that one off earlier. It was sort of 6 months, I think, is the general guidance. Paul, is that correct if the devices don't auto test?
Yes, I mean, the device will either have and if it's
Yeah, I think we're struggling to. Yeah, I think we're struggling to hear you, Paul. Yeah, I'll pick up the other questions, Paul, because I think Chris is with me, so I think my mic's okay. So I'll just try and pick up the others, and then anything I can't answer, we'll ask for your help with to come back to afterwards.
Sorry, before you go on, is that any better?
That's a lot better, thank you.
Okay, all right, let's try that. Just change move things around a bit. Okay, let's have a look at the next question then. We mentioned about testing and the 6 month, but there's a question about whether the testing of AFDDs is in the 18th edition. There's no testing procedure as such going to be in the 18th edition. So there is a check box on one of the reports that you have to fill out to say that if there's an AFDD present, but there are no actual tests that you can undertake, and there's no test procedure. Next question from Raphael is about in-service testing of electrical circuits, installation testing. The devices, as part of their design, are designed to withstand 500 volts. However, it is possible you could get erroneous readings. So really what you need to do is follow the manufacturer's instructions. And in those cases, it is recommended that electronic devices, not just AFDDs, but electronic devices of any form, of which these days there are many various shapes, sizes and types, it is recommended that these are disconnected during testing anyway, to avoid damage to any devices or products, but also to avoid erroneous results. Next question from Stuart is about TP&M boards and retrofit. Again, the expected, and we won't know for absolute certain until they're published, but the expected 18th edition only covers single phase at this point in time. So it only covers single phase applications. And retrofit, they're not really intended, principally intended to be retrofitted to existing boards, because they, in the main, will need a new busbar system or a different busbar system. But that's not to say manufacturers may provide some kind of retrofit kit, but that'll be entirely down to the manufacturer. Then somebody asked about discrimination. In terms of arc fault, there is no discrimination. So you would not put two arc fault devices in cascade or in series. So there's no need to do that. They're not like RCDs where you have different levels and time delays and such like. They work on one setting, if I can put it that way. So there's no requirements, or it's certainly not recommended that you cascade them in any form.
Yeah, probably worth adding to that as well, Paul. I think we touched on it earlier that if it was an arc fault device, you rightly were saying, I wouldn't expect those to cascade. If you'd got, let's just say, a device, however, where it had overcurrent protection integrated into it, we would then expect the manufacturer would provide the same information as you would do with an MCB today. So if, you know, in the case of Eaton, where we have what we refer to AFDD plus devices, we have characteristic curves that are available for those products. We have a braking capacity for that product as well, because it has an element of it, which is that normal overcurrent device. But as you say, Paul, if it's a standalone arc fault device, then that wouldn't be relevant.
Yeah, indeed. I mean, you know, if you've got if you're using the Eaton product and you've got an upstream protective device, be it a fuse or a circuit breaker, then yes, obviously discrimination is required, as the same as if you had an RCD upstream, where you have time delay RCD. But purely for the arc fault element, we certainly wouldn't put two in series. Therefore, no discrimination is applicable. Question concerning installation per circuit or per group of circuits, as is typical for RCDs in the UK, a lot of split load boards. The AFDD needs to be applied to each final circuit. There's no intention or purpose that it should be applied to a group of circuits. So it has to be applied to each final circuit. Just looking at the next question about the ring main, so ring circuit rather. And as someone has correctly, as Raphael has correctly identified, it does not detect an arc fault in the live conductor of a ring circuit. That is predominantly because there is barely, if any, arcing when there's a break in the live conductor of a ring circuit. Once you've got a break in that conductor, then the two live conductors effectively end up as two radials. So the ring has been broken, and any load would go down each leg of the radials. The neutral, if it's still intact, obviously would still be part of the ring, but there wouldn't be any arcing across the break in the leg of the ring circuit. So that yes, the device would not detect that, simply because there would be wouldn't be any arcing across that break. I think we've answered the. Somebody's asked, are we going to see the decline in the ring circuit? That is entirely up to how the installation practices go. That's not something we can answer at this point. But they are applicable. They are still applicable to ring circuits. And if I can just explain the other elements of ring circuits, they will detect a parallel fault within the ring. So if you have a parallel fault across 2 points of the ring, then the device will detect that. And the device will also detect any series or parallel arcs on equipment plugged into the ring. So if you have a piece of equipment plugged into a socket outlet, the device will detect a series fault in that instance or a parallel fault. It is only a parallel break, a series break rather, in the ring itself that will not be detected due to lack of arcing. Sorry, Mark, are you going to pick up on something?
Yeah, I was just said it's a good question on ring mains, and if anybody's in any doubt about it, I know we cover it off within the Beamer guide, don't we, Paul? So, if anybody can't quite remember the answer to the question, the Beamer guide's a good source of reference about, does an arc fault detection device detect a fault on ring main or not, or why does it behave in that way? So I was just going to mention that it's a good point of reference.
Yeah, indeed. There is as Mark has said, the guide available, and we are actually working or about to shortly release the second edition, which will have a little bit more information and a little more clarity. The first one, it did raise some questions. The first one, so nevertheless, it's there and it's a very useful document.
Yep.
Okay. I think we've covered them. There's some late questions coming in.
Yeah, I think there's one about testing in terms of how can you confidently test one, Paul, which is from David Stone.
Oh yeah. Well, again, there is no equipment. It's not like an RCD where you can go out and buy an RCD tester. There is no equipment on the market, and it would be very difficult to design such equipment, because obviously to test an arc fault detection device, you'd need to create an arc, and that is not a simple thing to do. So there's no installation test equipment, but the device, as I say, does either have a test button or has automatic testing. Now you might think, well, surely we should be testing these devices with an installation tester, as we do with RCDs. But there are a number of products out there that we don't test. They work perfectly well. There's no requirement to test them, and AFDDs are in the same vein.
I think there's
Sorry, go on.
I think there's a couple of questions about the size of equipment. I think I missed it there from a Stuart about practically how you'd fit a device with a three-phase board. I think in that sort of scenario, Paul, I mean, I've certainly worked within business in the past where there have been devices where they are not the same footprint as a standard MCB, where they have been mounted within extension boxes and then fed via a terminal block, so it was deemed to be within a fault-free zone. So I guess that could be one practical way of achieving arc fault devices on certain circuits within a three-phase board. So it's probably one example I might give about how it might be approached in the short term. I think there's it sort of links into that. There's a comment by Gavin around boards being huge if you've got arc fault devices on every circuit. I think on that, again, I'd just say first of all, it depends on the building. So we're not sort of saying that every building would necessarily need to have them. It depends on the building. What I'd probably then sort of say is that it then depends maybe on some of the circuits within those buildings. Ultimately, in the short term, it could be that distribution boards, do become larger. My own personal opinion would be it would be a small price to pay if we got high levels of safety from that. But probably what I would also sort of say is that, if we think about other technologies and most technology in life, it becomes miniaturized over the passage of time. So, we've put a few examples upon screen where you're adding devices onto other devices, or the device itself is larger than we see today. I'm sure as we move forwards, physically things will become smaller. One of the things we have to consider is that, for some arc fault detection device you'll see in the market today, they are, they're not dissimilar in size to an MCB, for example, but that does then constrain their current carrying capacity, and would then preclude their use from a 32 amp ring main. if you're looking at a 32 amp ring main, it would tend to be a larger product than we traditionally use. But as I say, for me, it's a small price to pay in the short term, and that won't be forever. I'm sure we'll see products get smaller as we move forwards.
Okay. I think, have we covered all the questions?
Yeah, there's just yeah, there's I'll just answer this question about pricing, which it wouldn't be one for us to quote exact pound value on the webinar today, but I think Raphael's probably summarised it quite well in almost a response to his own question, that we're talking about new technology. New technology, again, no matter what it is, comes with a premium. When you look at it, the cost of our fault detection devices, for me, I would say that it's a small price to pay versus some of the benefits. If you look at the price for a given circuit over the lifetime of that installation, you're talking, I think it's less than half a pence per day, typically. But I think, as Raphael also said, there will be a price point in the marketplace initially, but over the passage of time, that price will fall because most technology tends to do that. So I think it's value from I think you'll find a price once technology comes into the market over the coming weeks, which is affordable. But ultimately, that marketplace will become more competitive, and prices will fall as it always does with all technology.
And just picking up on the comments and question from Adrian regarding series fault and neutrals. Yes, they will. AFDDs will detect a series fault, series arcing in the live or neutral leg. So it's not designed just to pick up live. It detects arcs in either live or neutral.
Cool. Thank you, Paul, very much for your help. It's really appreciated again. Just to wrap up this afternoon, we're finishing pretty much bang on time, actually. I'd just like to again thank everybody for attending this afternoon. I hope you found the session useful. To recap on next steps, so the webinar, if you want to share it with any colleagues, friends, family, it will be available from Voltimum very shortly, within the next couple of days. Around CPD accreditation, for anybody that's attended today, we will share your details directly with CPD, so you'll get the accreditation for that, and then as certificates will be issued digitally. You could expect to receive those within the next 2 weeks. We did run this seminar a few weeks back. It was really popular, hence why we've run it again. I think actually the certificates came out within about 3 to 4 days. We did have one gentleman where I think his certificate got blocked by spam mail, so just spam filters rather. So just keep your eyes open for that. But if you've got any problems at all, I'm relatively active on LinkedIn. If you're wondering where's your certificate, you've not had it, please get in contact with me and I'll sort things out for you. So thank you for this afternoon. Really appreciate your attendance, and hopefully we get the chance to speak to you again in the near future. Thank you.